Well, I'll just briefly reprise my viewpoint. My viewpoint is that the true nature of infinity is it's not a very large number. It's an entity that can never, ever be attained. It's always beyond the bounds of the possible. And therefore, the claimed existence of physical existing infinities is problematic because it's an unattainable state rather than a number. And I quote David Hilbert, "The infinite is nowhere to be found in reality, no matter what experiences, observation, and knowledge are appealed to." Notice he says in reality. So claimed infinities are not scientific claims. If science involves testability by either observation or experiment, because even if they did exist, there's no way you can prove they exist, because it's just impossible to have an experiment or even an observation which will prove an infinity exists. And yes, of course, it's useful in some mathematical context. What's its relation to physical reality? I'm suggesting these basic guidelines. What I call Hilbert's golden rule: infinities do not exist in real physical systems. And so that leads to the infinity fork. If the use of the infinity in physics is use of the essential problems of infinity, that's its paradoxical properties, then in my opinion the argument should be discarded. If the use is not its essential properties, but just the fact that it's really a very large number, then you should replace it by that very large number. And working out what that large number is will in fact tell you interesting things about the physics that is going on. I just want to return to the business of eternal inflation. And our speaker yesterday very nicely talked about how infinite spaces could exist because all time surfaces are equal in general relativity, so you could regard that time surface as equal to that one. I disagree on that. In my opinion, in the real universe, preferred surfaces exist because preferred lines exist. And a proposal I've put in that archive paper there is that in the real universe, what you need to do, start at the beginning of the universe. There are preferred time-like lines, which are the Ricci eigenlines. That is the average motion of matter in the universe. And what you need to do is measure proper time along these Ricci timelines, and that gives you a preferred surface of proper time. That, in fact, this is, when you talk about the age of the universe or the age of objects in the universe, that is the time you're talking about. That gives you preferred surfaces. And those surfaces, because this is a de Sitter space-time, it's identified like those are compact, everything is finite. And what happens is, as time goes on, this surface moves up and we see more and more of it, but we're never at any finite time does this full surface ever come into existence. It hasn't become real, that surface. What is real is what's in the past there. This is the potential in the future. This potential is moving up, and at no finite time does all of this infinite surface actually exist. And that's the viewpoint put in this paper on the archive. Infinity is never attained. It's always in the future something which you are working towards. So this is my response to that yesterday. It's dealt in much greater detail in that archive argument. Okay, I want to talk about infinities of size, and this is the idea of small universes. Yesterday I mentioned, I repeat, Einstein equations are local equations. They determine the local geometry, not the global topology. In a standard Robertson-Walker space-time, you've got the cosmic time direct product with a spatial section, and that spatial section is covering space as Euclidean space or a sphere or a hyperbolic space. But it can be compact for finite universes if the topology is closed, and there's no reason in general relativity why it has to have that simply connected topology. And I mentioned that yesterday. The new question today is, can we test this observationally? And we can if the identification scale is smaller than the visual horizon. In that case, you get multiple images, and it's like in this room, if you were to put mirrors on all of the walls, the floor, and the ceiling, and you had a finite number of galaxies, you would apparently see the galaxies stretching off forever. It would look like an arbitrary large universe, even though it was a small number with mirrors, and that's what it looks like. So I showed this picture last time. You have a unit cell on the right, you identify it, and it's got a compact space section, but you can unwrap it to get the universal covering space, and in that universal covering space there's a group of identifications. So that cell is repeated numerous times, and you choose one of them arbitrarily as being your center. So there's repetition of a basic unit cell with the opposite edge identified. It creates an effectively infinite universe because this space section effectively goes on forever. Now, if we're sitting at this point there and we look back in the past, our light cone spreads out. We see that at one time. We see larger and larger parts of this identified space. if we see that radius, that's the first time we see multiple images. If we go to that radius, every single entity in the unit cell has multiple images. If we go out to that size, there are many images of each object in the universe. And so when you look to different redshifts, you see to different distances. If the visual horizon was very small, you wouldn't see any multiple images. If it's the same size roughly as the identification scale, you see some multiple images, and if it's much larger, you see many multiple images. And so the key issue is the visual horizon larger or smaller than these scales that occur? And in a space-time diagram, this is what it looks like. You've got your past light cone, and you identify those two lines. Those are the same galaxy, and so you see it on the left, and you see it on the right. So you get multiple images of the same galaxy, including our own. And that's one of the wonderful things about this. If this was to happen, we would be able to see our own galaxy many places out there at different stages in its history. And that would turn the study of galactic evolution into an observational study, because we'd see our own galaxy at different times in the past. And so the same galaxy occurs there. You see it at different times. You see it at different redshifts. If you observe that one there, it's at one redshift there, it's at a different redshift there, although it's the same galaxy seen in that direction and that direction. And so in a small universe with a torus topology, you identify like that, and then if there's a star there, you can see it the direct route, or you can see it by going around. And so you get multiple images. Of course, the torus topology is the simplest possible topology that you can get. This is a simulation I did many years ago with a student, 30 galaxies in a universe with a cutoff redshift of 0.5 and a torus topology on the left. The identification scale there was 800 megaparsecs, and the 30 galaxies give you 683 images, and it's got a rather nice structure, rather like those voids and walls which you seem to see in the large-scale structure. The one on the right is the same but a different topology. All of the spaces are twisted by 180 degrees. So the one on the left is a torus, and the one on the right there twisted by 180 degrees, each of the faces, and so there's 683 images of the 30 galaxies on the left and 679 on the right. And you can see it's really a rather nice kind of thing that you're getting there. But there are many much more complex possibilities, and this paper, Cosmic Topology by Lachaise, Ray and Luminet, Physics Reports, is a very good summary, and another nice one by Jan Levin, also in Physics Reports. And I can't go through all the details of this, I just want to give a flavor of this. And these slides are from Jean-Philippe Uzan in 2 dimensions. You have a cylinder, you have a Möbius strip, you have a torus, and you have a Klein bottle. And 2 of them are orientable and 2 of them are not. But of course we want the 3-dimensional one. In 3-dimensional Euclidean spaces, there are the compact ones on the left, the non-compact ones on the right. I'm interested in the compact ones. And there's a 3 torus, a quartus turn, a half turn, a 6th turn space, a twist turn space. There's a whole lot of possibilities, but you can number them, and it's a finite set of possibilities in the case of Euclidean space. And to repeat again, we don't know any principle from the Einstein equations why any one of these is preferred to any other ones. It would really be a fantastic thing to come up with something, to maximize something which would choose one of these topologies over the others. But in Euclidean manifolds, there are 18 types. In the hyperbolic manifolds, there's an infinity of types, and there's a whole catalogue of these things which Weeks has put together. They are very, very complicated. The spherical manifolds, there's a countable infinity. This is really a complicated subject. The first complete classification was in the 1930s. It's been revised in terms of quaternions in that paper that I quote up there. And what you're actually having to do is to determine all the finite subgroups of SO4 for the 3D spherical places. And there's 2 countable infinite families, the lens spaces and the prism spaces, and then 3 special ones. So this is the kind of thing that you get into. What you get is, it's like, as I said, a repeated structure there. So the question is, can you see it? And if you plot a power spectrum of galaxies, you're going to get spikes there because there's a symmetry there. I've already mentioned the symmetry. And so the distances between these galaxies are the same when you apply the group operation. The distance is invariant, and that's the group. There will be a symmetry in the distances when you apply the group, which is the group of identifications. And so you get spikes related to that. And this has been studied in a great lot of depth. You can calculate the cosmic microwave background in these spaces, and this is quite complicated because you have got to find eigenmodes of this equation which involves the curvature, but the point about it is those eigenmodes have to be compatible with these different topologies. Now that's relatively easy in the case of the Euclidean spaces, but in the case of the hyperbolic spaces this is a really very, very difficult study. Your modes are very complicated because you've got very, very complex boundary conditions, but these have been attained for all flat spaces, almost all spherical spaces. A special case which has been looked at by some of my colleagues, by the way, the person I've looked at most of this is Jean-Philippe Uzan, who's done some really nice work on this, is a dodecahedral space topology. And it explains the weak wide-angle temperature correlations in the cosmic microwave background. What you've got there is your fundamental cell is a dodecahedron, and you can fit that together with 120 copies, which will give you a 3-sphere, and it's got a holonomic group of order 120. It's a very beautiful space because it's extremely rigid. There's very, very little freedom in this particular it's a 3-sphere identified in this kind of way, and you can work out the spectrum of the Laplacian. And what it does particularly for you is there's this thing which is hidden away, which people don't often talk about. At the far end, at the large scales, this beautiful theory doesn't quite fit. Now, one of the big questions there is, do we have to explain that or not? Do we say it's just a statistical fluke? It's cosmic variance. Well, maybe it is just a statistical fluke, but a small universe, because it's closed, it predicts there will be a drop-off in the power spectrum at large scales. And in particular in the dodecahedral space, you get a best fit to these points, which are below what the standard model says. For a density parameter, very precise, omega is 1.013. Now, you may tell me that that perhaps has been excluded, or maybe you won't. But the point about this is good science. It's fantastic calculations. It's related to observation. It's a possible situation. And the observations are going to tell us whether this works or not. The most important way of detecting the topologies is circles in the sky, which was pointed out by Cornish, Spergel, and Starkman. Because when you look down to the last scattering surface, because they're identifications, you see circles in the microwave background which are identical in different directions in the sky. And the last scattering surface can self-intersect with the past light cone, so there are matched circles. The correlation is strict for the Sachs-Wolf term, but the Doppler and integrated Sachs-Wolf terms throw noise in on top of that, and a lot of studies have been done on this. This is a picture there, in which case you can see that there are two identical circles, and you can see those patterns are repeated because there's this identification. And this is the kind of simulation which has been done. It's a very complicated search. It's a 6-parameter search of the cosmic background radiation data, of the full data across the spire. You can't get this from the power spectrum. You've got to search the actual data. What you've got to do to get two matched circles, you've got to find the position of the circles, the radius of the circles, and they can be twisted relative to each other. So it's a 6-parameter search. And the best algorithm runs as n to the 15th times the logarithm of the number of pixels, and there's a very, very large number of pixels in those maths. So what has happened is most of the searches have been restricted to back-to-back circles, in which there are only 3 parameters. And so most of those searches have disproved this case in that case, but that's a very small subspace of the full set of possibilities. And so what you need to do is you need to use the angular power spectrum to exclude as much of the spaces as possible, and then select the best candidate to try with this detailed search. And I must emphasize, when you do the search, you don't have to assume what the topology is beforehand. You do the search. If you find these matched circles, the topology is one of the things you work out from it. It's one of the very beautiful results. There are particular patterns of matched circles, and if you know that, if you find them, they will tell you what the topology is. And this is a typical paper by Starkman, Cornish, Spergel et al. We present an up-to-date update to the search for a non-trivial topology of the universe by searching for matched circle pairs in the cosmic microwave background using the WMAP 7-year data. This may all change in 2 days' time. We extend the existing bounds to encompass a wider range of possible topologies by searching for matched circle pairs with opening angles 10 degrees less than 90 and separation angles 11 less than 180. The extended search revealed 2 small anomalous regions in the sky. Numerous pairs of well-matched circles are found where both circles pass through one or other of those regions. As this is not the signature of any known manifold, but is a likely consequence of contamination, we repeat the search, and so on. We find no statistically significant pairs of matched circles, and so no hints of a non-trivial topology. The absence of matched circles increases the lower limit on the length of the shortest closed null geodesics that self-intersects at our location in the universe. Equivalently, the injectivity radius at our location to 98.5% of the diameter of the last scattering surface, or approximately 26 gigaparsec. It extends the limit to any manifolds in which the intersecting arcs of said geodesic form an angle greater than 10. Well, this is a very disappointing result from my viewpoint, but I'll emphasize this is good science. It's a really interesting proposal. It's proper observational stuff that's going on. And the situation at the moment, and I don't know what will be said in a few days' time, the WMAC constraint that we've had up to now is 85% of the size of the last scattering surface. And so it's still possible, according to that it is, but it would be 85% of the last scattering surface. Using the correlation matrix idea, because you can get hints of the structure on bigger than the scale because of the way it affects structure formation, you can extend to 100 to 110 to 120% of the last scattering surface scale. But what you cannot do is detect in this method anything larger than 2. So if the identification scale is twice the size of the last scattering surface, we cannot observationally detect it in any way. So are there small universes? The thing about them, they actually, philosophically speaking, they're fantastic. These are the universes in which we have already seen everything that exists in the universe. So it's unlike all of those other ones where there's all of this stuff further and further out beyond the horizon. Everything is within the horizon. So incidentally, then there's no infinity, there's no multiverse. So if we ever verify this, we will have disproved the simple versions, the connected versions of the multiverse idea. You see right around, you get the illusion of infinity. It's the only truly observable universe. As I've said, it's the only ones where we see everything that exists, and this is perfectly possible. Galactic history is an observational science. I've mentioned that in principle we can see our own galaxy at different directions in the sky at different times in our past history. But also these are the only models where we can strictly predict the future, because normally what happens, we're here, this is our past light cone, that's the limit of what we can see. Now, as we heard yesterday, at a later time we see further out. If a domain wall came smashing into us, which is perfectly possible, as we were hearing yesterday, there are these bubbles which might interact with each other. There could be this thing coming in. What we knew yesterday does not guarantee that this won't happen tomorrow, and this thing could come in and smash the solar system apart or something of the sort. The only case in which we can actually predict the future is in the small universes, because then we've seen already everything there is, and we know that there isn't such a domain wall about to come in because we've already seen everything that exists. And so it's the only universes where we can actually be totally certain that Halley's comet will return, that the sun will rise, and all the rest of it. So there's a cutoff in the large-scale power spectrum. You can test it by galaxies and sources. That's not easy. I didn't talk much about that. The problem with using galaxies is the same old problem as always, galactic evolution. And so it's, in principle, you could identify the same cluster over there as over there, but you see them at different times in their histories from different directions with different absorption and so on. It's very difficult actually to identify the same clusters directly, and that's why the circles in the sky is the most important one. So my conclusion of all of this, it may or may not be the case we live in a small universe. It's good science, it's testable, it's a very interesting idea. I would like it to be true, but if it isn't true, it's an important thing to look at, because the nature of the universe, the nature of our relation to the universe, the epistemology of cosmology is completely different in a small universe than otherwise. Okay, I want to change to a completely different topic, which is infinity and isolated local systems. And this is that old chestnut: how does the global expansion affect local physics? Can we detect the Hubble constant in the solar system? Well, like all local condensations, we've actually opted out of the global expansion. Matter's recollapsed to an isolated system that's unaffected by the cosmic expansion. Like an expanding gas doesn't change the atoms in it. Now, a key feature in this is that we're an isolated system in the universe. The universe allows us to exist as an isolated system. The universe doesn't interfere with us. It will be perfectly possible, and we already mentioned that in the last one, that gravitational waves were coming in, or cosmic rays, or black holes, rapidly changing tidal forces. There's many, many ways in which the universe could interfere with us and prevent the solar system from actually being a tidal system. In fact, the solar system probably wouldn't exist. Now, the standard analysis of asymptotically flat systems doesn't help us. The standard analysis is so beautifully done in terms of SCRI, the conformal infinity, and all of the relativists have seen this diagram, that this is conformal null infinity, that's time-like infinity, that's space-like infinity. We've gone to conformal coordinates, and the whole of space-time is represented there in arctan transformation. So that's infinity, that's minus infinity, that's infinity, and this is your system. And this is a representation which is standardly used to analyze asymptotically flat systems, outgoing gravitational radiation, mass at infinity, and all the rest of it. The problem with that, it's an infinitely inaccurate representation of the real universe, because the real universe is not, we believe, asymptotically flat. In reality, there isn't any point I naught, there isn't any point I minus. And so one's analyzing asymptotically flat systems using a very beautiful approximation, but it's not, in some sense, a good approximation. So many years ago, I suggested we should instead put boundary conditions on all fields at a finite distance rather than infinity itself. And that leads to the concept of what I called a finite infinity, or phi. Now, what this is, it's a smooth time-like surface at a large but finite distance r from the center of the system considered, separating it from the surrounding universe, lying in an almost flat space-time region. So we want to talk about radiation from a binary pulsar. You're surrounded by a sphere, or you want to talk about the future of solar system. You're surrounded by a sphere which separates us from the outside universe. And the point about that is when you do that, you can talk about what comes in and out across that sphere. You can talk about the interaction of the system with the universe outside, and you can't do that if you've gone to infinity with this very inaccurate representation of the real universe. So you can consider the ways the universe influences us across the surface and how we influence the universe. And so this is the idea that here's the system you want to talk about, like the solar system. You're surrounded by the sphere. Now, for the solar system, I'm going to suggest that 2 light years is a good distance to use. I'll say a bit more about that in a minute. The rest of the universe out there is not asymptotically flat. Why? Because there's other stars out there, there's galaxies out there, there's voids out there, there's all sorts of other stuff out there. But if you want to talk about this system here, it's good physics to talk about what happens within the sphere and to say we don't need to know what happens outside, and to use the sphere to separate you, because then you can talk about what comes in, cosmic rays, black holes, gravitational waves, what goes out, cosmic rays, black holes, and all the rest of it. You can talk and analyze, and you can talk about what kinds of limits on incoming stuff still allow you to talk about this as an isolated system. There'll be a bound on how much stuff coming in allows you to talk about it as isolated. Of course, we're not isolated. The cosmic microwave background radiation is coming in. Cosmic rays are coming in and so on, but they're not coming in sufficient density to stop us talking about ourselves as basically an isolated system. And so this is an epsilon and delta situation. You can talk about how big the perturbations are to enable you to think of this as isolated. Now, if you take the Schwarzschild factor with the sun's radius, I suggest finite infinity is a half 4.2 light years, because 4.2 light years is the distance to the nearest star, about 2.1 light years. And in that case, the Schwarzschild factor is 1 minus 2.6 times 10 to the minus 13. So you're asymptotically flat to very, very high accuracy on that surface. And so that's what I suggest is the finite infinity. It's the sphere on which you should put it. Now, one thing about this, from a general relativity viewpoint, what happens is very interesting. Because what affects the solar system here, I'll talk about this in a minute. We want to talk about the solar system, let's say, for 300 years. This is 2 light years across, but 300 years this way. So it's an incredibly thin tube. That means from a general relativity viewpoint, the real initial value problem is the null initial value problem. This time-like part is way, way back in the past, and it's a very small part of that boundary in some sense. Nevertheless, in many ways, it's the most important part, which is something I will talk about in just a minute. So the point about this, once you've got finite infinity, you can talk about mass, energy, momentum. You can use all the standard definitions. Now the standard definitions, the ADM and the Bondi and Sachs definitions, the ADM masses you evaluate it at infinity, and the Bondi Sachs et al. Definitions you evaluate mass and energy at infinity. I'm saying don't evaluate it at infinity, evaluate it at this finite distance. And this is an example of the inessential use of infinity. People talk about infinity. You're not using any of the paradoxical properties of infinity. You're just using infinity to stand for a very large number. So this is where my philosophy is. Don't do that. Talk about the real numbers. Talk about how far away it is. And then you can do physics talking about how big the perturbations are on that surface. And so this is the inessential use of infinity. Replace it by the value at phi and you can do good physics. You can determine mass, energy, incoming and outgoing radiation. Now there is of course a whole literature on quasi-local definitions. And this is something slightly different. The quasi-local definitions, you're trying to go right into the system. Here you're using the asymptotic definitions but not at infinity, at a very, very large distance. So it's not quite the same as the quasi-local definitions. Now, let's go back to this question. What is the really relevant domain? In that domain, what are the conditions which lead to galaxies, stars, and planets? And in fact, it's very, very local. If you ask which part of the universe affects what's happening in this room at this moment, what has made the existence of this room possible? It's the origin of the elements, the origin of first-generation stars and galaxies, the origin of second-generation stars and galaxies. We can only look on the past light cone and we can see all of that stuff out there, but all of that stuff is irrelevant to what's going on in this room. I love to draw these past light cones, but they don't matter in a certain sense. What matters is the start of the universe, because if we didn't start there, we wouldn't be up here, and what matters is stuff like nucleosynthesis. What happens there matters up there, but that stuff does not matter. You have to use incredibly accurate detectors to find out what's going there. It has no effect on the practical everyday world. What matters in this room is not conditions on the past null cone, nor at infinity. The tensor modes which come up the null cone are determined by distant matter, because the corresponding characteristic velocity is the speed of light. But in the case of pressure-free matter, the recent universe, the characteristic velocities of the scalar and vector modes are zero because they're pressure-free. So they're only directly affected by very, very nearby matter. The tensor modes are negligible, as is radiation from outside the solar system. And the true domain of dependence, the physical domain of dependence, what affects what happens in this room, is something like a co-moving sphere of size 2 megaparsecs. And this is a diagram I put together with Bill Sturger to illustrate this. This is going back. That's the last scattering surface. Cold dot matter decoupling, horizon exit, horizon entry, the quantum scale. What happens here is affected by what lies within this, which is the area from which geological data there are determined. Matter there is conserved and it goes up to there. That's what matters up here. It doesn't matter what happened over there. And so this is the idea of the physical horizon. It's the part of the universe which has actually affected what's happening here and now in this room. All of the stuff out there doesn't matter. It's made no effect whatever. So for the domains for the system, the finite infinity is the present system boundary 2 light years. In terms of talking about us as an isolated system, that's a good place to go. If you want to measure the mass of the sun from the asymptotics of the system, that's a good place to go. If you go further out, you're going to get interference from other stars and other stuff. If you want to talk about what happened in the past, where did we all come from? It's this larger sphere. So this is this boundary. Everything inside there affected what's happening in this room today. Everything outside there had no effect whatever. And in particular, what happened at infinity has no effect on what's happening at this room, if there is an infinity. And so the true domain of dependence, the physical one which actually affects us, is a co-moving sphere of size 2 megaparsecs to date. That's what I'm suggesting. And all the rest is irrelevant. We don't need the rest of the visible universe, let alone any hypothetical infinities outside, because they don't affect us. Okay. Now, where this becomes interesting is if we apply these ideas to black holes, because there's a standard definition of black holes requires knowing the infinite future, which we don't know. And in a certain sense, that wonderful, beautiful theory of black holes, it doesn't apply to astrophysical black holes, because no astrophysicist knows what's going to happen in the infinite future of the universe, which is what you need to do to get the real definition of the event horizon. You don't know where the event horizon is until the universe has run its course to the end. And so you don't know today where the event horizon is. But we want to talk about black holes existing in the center of our galaxy, other galaxies. How can we do that if we don't know what's going to happen in the infinite future? We need a definition that does not depend on the infinite future, an astrophysically realistic and relevant definition, which in principle, the astrophysicists are in principle using such a definition, but we don't actually have, from the relativity side, a proper definition of black holes which doesn't depend on infinities and therefore is unrealistic. What we need is something like what I was saying about the finite infinity related to the black holes, and we need to be able to say something like, after what time has a black hole formed as a star is going? So we need something like the following. I haven't developed this properly. And astrophysically relevant black holes. We need to surround this collapsing system by a sphere of area 4 pi r squared that separates the system from the rest of the universe at some time t naught. So you start off at a time t naught when there isn't a black hole. You can see that there isn't a black hole. You choose the sphere such that light emitted from within after a time t naught never crosses the sphere with an astrophysically relevant time TBH after that. And so, sorry, I should have said there, it's the minimum 2 sphere. It's the minimum 2 sphere, such that light emitted from within, after the time you started looking at it, never reaches the system within an astrophysically relevant time. So what time should you choose? Well, maybe 10 to the 9th years. This thing has been emitting light, and if the light it's emitted hasn't after 10 to the 9th years reached the sphere, then it isn't ever going to make it. Now that's an astrophysical statement. It's not a 100% tight, rigorous statement. But for instance, light from the sun reaches the edge of the solar system in 0.0032 years. If the light hadn't reached this sphere after 10 to the 9 years, you're entitled to say this is a trapped surface. The interior is not affecting the exterior. This is a black hole for all purposes. And so this is the kind of thing which I'm suggesting one needs here is put in the numbers, and the numbers are telling you interesting things, and this is far more useful in some sense than having that infinity, which prevents you thinking about what these numbers are. So the relative domain, the relevant domains are not infinity. At the present, its asymptotic flatness at a finite infinity enables you to talk about stuff coming in and out and whether we are actually an isolated system, how much incoming stuff would prevent us any longer talking about being an isolated system. You can find the mass inflows, the outflows, and the interaction with the universe. You can't do that if you insist on the infinity involved in scrying. In the past, the physics horizon, there's 2 megaparsecs. All that effectively influences lies inside there, and any stuff outside there is in a certain sense irrelevant. Look, I don't want to push that too far, but you can see what I'm talking about. And I'm suggesting that black hole theory should be realistic in this kind of way. It is in practice, because the people who do astrophysical black holes don't worry about the infinite future. They don't say we can't say there's a black hole at the center of the galaxy until time has elapsed. And so what we actually need is a realistic one which needs this kind of finite infinity idea. And this one is infinities of age. I'm going to be rather brief. Will the universe be infinite in the future? Well, it depends on the equation of state, of the dark energy, if there is dark energy, and the spatial curvature. And I do want to emphasize one thing here. For any realistic matter, whether we recollapse in the future or not depends on k. We only recollapse if k is positive. And so one of the most important things you can determine from astronomical observations is the sign of k. If k comes out negative, then the universe will expand forever no matter what the matter does, assuming the energy density of matter stays positive, which I'm going to be assuming. If the dark energy is lambda, the observable universe will be infinite in the future. And so that's a pretty straightforward statement. But we'll never get there, and this comes back to my statement. The universe will be infinite, but that infinity is always to be attained. It never has been attained. It's always something which you're going towards. The universe will expand, lambda will will dominate it. It'll always be getting bigger and bigger, but at no time will it actually have reached infinity, because no matter how long it expanded, infinity has never been reached. And this is the sense in which the infinity, it's a theoretical concept. The infinity, which is up there, which we can do in those nice diagrams, doesn't actually exist in the physical world at any time that we can do any measurements. We'll never get it there, but it'll always be in the future. Those nice conformal diagrams represent events that never arise. They're always going to happen. There's not a realized infinity at any finite time in the future. What about the past? What about bounces and phoenix universes? Well, these are conceivable. And there have been many, many proposals like that. There's this beautiful article by Peebles way back about phoenix universes. But you get this problem, which Tolman already talked about, Penrose has talked about. If you get a bounce, inhomogeneities grow, and your problem if you get a bounce, how do you smooth the thing out as you go through the bounce? Unless some mechanism resets the system, you end up with a very, very inhomogeneous state. And so there are all these proposals, pre-bang, ekpyrotic, cyclic, Roger Penrose. Now the first point is these can never be exact. There will never be an exact cyclic universe. That's a mirage. It isn't even conceivable there could be actually cyclic universes, that you would get exactly the same state. I think that's just totally out of the question. We can imagine hypothetical matter that will give you a bounce, and all of these various proposals in one way or another have hypothetical matter to give you a bounce, but that matter is nothing like we've ever seen before. There's not the slightest evidence that such matter actually exists. You can postulate matter which would lead to a bounce. You have to have negative kinetic energy terms in some sense or other. We've never encountered any matter like this. You can write down Lagrangians. There's no reason to believe that such matter actually exists, even though you can write down hypothetical Lagrangians for it. Or else there will be some uncaused event like Roger Penrose's one. Roger Penrose's conformal cyclic cosmologies, it's a beautiful picture, but he doesn't have a mechanism which links you from the one epoch to the next one. It was mentioned yesterday, this idea I worked on emergent from an Einstein static state. Maybe we were Einstein static forever, but then, as was said, any time it starts expanding, why didn't it happen before? And I have to admit that's a pretty good problem. Is it stable? It may not be stable. So it's worth pursuing, but I'm not going to say too much. This is, of course, the old Eddington-Lemaitre model updated. It's about as plausible as any of those bounce models, and none of them are, in my opinion, very plausible. If the universe does last forever, we have this terrible problem which is claimed of the eternal return, the alleged Boltzmann brains popping out of the vacuum. I'm just going to say a very skeptical remark. I don't believe any of that stuff about Boltzmann brains popping out of the vacuum for a great many reasons. For instance, I don't think that there's a Hilbert space for chickens. I don't think there's a creation operator for chickens. I think this is something which is just kind of, I don't believe it, but anyhow. But also, supposing there was an infinite universe, would you really want an infinite life? The philosophical question. If we could live forever, and we somehow sorted out so that we did live forever, there's a finite number of thoughts we can think, because the brain is a finite state machine. You do get the eternal return coming. After a certain time, you would have thought all possible thoughts. You'd have to rethink those thoughts. If you could live forever, you would rethink the same set of thoughts infinitely often. And that's actually a very, very depressing kind of concept if you think about it. Luckily, you wouldn't remember that you'd thought them, because the brain can only remember a finite number of events. But from a philosophical viewpoint, again, and this is philosophy, it's not science, it's actually not such a nice idea, the idea that we would live forever, because actually you would then be, as far as I can see, you would be in the eternal return situation. So the infinities of age, I don't think that it is infinite in the past. The attempts, in my opinion, the attempts to get a bounce all rely on implausible hypothetical matter. Just because you can dream up a weird Lagrangian does not prove such matter actually exists. It's all speculative, extrapolating known physics to the unknown beyond experimental tests. What is interesting is the idea that we emerged a finite time ago from a different kind of state where time did not exist, where there was a Euclidean space-time or quantum gravity phone or discrete space-time structure, something like that. It's obviously as worth pursuing all of this, but it's going to be very difficult to test any of that, to bring it into the domain of testable science. So my finite section is the infinities of size, the very small. I'd return to the claimed existence of physically existing infinities is not plausible in my opinion. Infinity is an unattainable statement. It's not a scientific statement. And one of the worst infinities in physics is the claim that there's an uncountable infinity of points between my fingers, of physically existing points. It's the physically existing which matters. Mathematically you can model it that way, but are there physically meaningful, distinct, uncountable infinities of points between my fingers? It has to be wrong, in my opinion. It just isn't even conceivably right. Is it plausible that the infinities of the mathematical number continuum exist in physical reality? It's much more plausible that space-time is discrete at the bottom in one form or other, and that an apparent continuity emerges on coarse graining like the air in this room, which seems perfectly continuous, but of course it isn't, it's discrete. And so the basic idea, Feynman said the most important statement that a physicist could leave to future generations was that matter is made of atoms. His statement was, if he had to leave one sentence for future generations, that would be the most important statement. I think that Hilbert statement about no infinities, plus the basic idea of quantum physics, that quantum stuff, things are discrete out there, and it's a philosophical position. I'm making it as a kind of an assumption that this is the way it should be, that space-time is also made of atoms, atoms of space-time. And so this takes the quantum principle and said it applies to everything else. It should apply to space-time as well as applying to matter. The consequences, well, there'll be no infinities, none of these infinities in space-time, because you'd have a discrete number of points, you'd have a finite number of points between my fingers, not an infinite number of points. If you take this viewpoint, I must emphasize, I want the discreteness to be there at the foundations. I want your model of space-time to start off discrete. I don't want you to take, like loop quantum gravity, a continuous model and then say we can find the space-time as quantized, because that's actually not a consistent position, because you start off with a continuum space-time and say, look, actually it's discrete. If you've done that, you must now go back to the start and start off with a discrete foundations and say, look, the discrete thing is self-consistent. If there's the discreteness, there's no uncountable infinity of points. And the emergent continuum space-time is apparent continuity, apparent Lorentz invariance come as a coarse-grained phenomenon. And the people who, in my opinion, have got closest to this are the people looking at causal set theory. Dowker, Henson, Sorkin, and others with those references which I give there. They start off with a discrete space-time structure and then with interactions between them, and then you try to produce a continuum structure to emerge out of it. Now, I know that's difficult, but I think that that difficulty is essential. I think this is the way to go, that it should be a foundational principle that the thing is discrete at the foundations. But, of course, causal set theory, it's based on conformal structure. You need something in addition to causal conformal structure. And also, one thinks there the thing being discrete in space, but of course, space-time, it also should be discrete in time. Was there an infinite number of points of time between a minute ago and now? For exactly the same kind of reason, also the time one should also be discrete. Space and time should be discrete, not just space. And as I emphasize, in my opinion, what we need to do, and I haven't worked on this myself, this is my position as an outsider, is derive a theory of space-time where the basic structure is discrete. It's not something where you say we can show it's discrete once we've started off on a continuum basis. How small should the discrete size be? Well, the obvious choice is the Planck length. And there's a nice article about minimum length from quantum mechanics and classical general relativity, how you measure it. We derive fundamental limits of measurements of position arising from quantum mechanics and classical GR. We show a primitive probe or target used in an experiment must be larger than the Planck length. This suggests a Planck size minimum ball of uncertainty in any measurement. We study interferometers whose precision is much finer than the size of any individual component, and tests are not obviously limited by the minimum ball. Nevertheless, we deduce a fundamental limit on the accuracy of order LP. Our results imply a device-independent limit on measurement. So that is an epistemological statement. And I'm saying, let's take that seriously and say it's not just epistemological, it's ontological. That actually is the minimum size. It's not just the minimum size that we can measure. So the hypothesis there would be that space-time is discrete at the bottom. Physics that is continuous for all practical purposes emerges because the measuring apparatus necessarily coarse grains. And again, I come back to that. If you claim it's continuous, it's not testable. It's not a scientific claim. Can you test the discreteness? And there is one way which people have tried, which is a very interesting one. If you look at very, very large distances, very distant objects, then you've traveled through a very long distance, and maybe the discreteness of space-time would interfere with our measurements of really, really distant astronomical objects. And so the kind of paper that looks at this is this paper, Energy Momentum Diffusion from Space-Time Discreteness, which would affect very, very distant measurements. There are probably people in this room who know far more than I do about this. All I'm saying is this is an important topic, because this is perhaps the one way which you can try to detect such discreteness. It was pointed out to me yesterday that David Tong has a paper, Physics in the Integers, where he says problems arise when we think of discretizing fermions. The problem comes when the interaction of the electron depends on the way it's spinning. This happens in the weak force. The force is mediated by the W boson. The W boson interacts differently with electrons that are spinning clockwise and those that are spinning anti-clockwise. Theories that treat clockwise and anti-clockwise spinning particles are said to be chiral, differently are chiral. No one knows how to formulate those on a computer. The obstacles that lie behind attempts to discretize chiral fermions are related to aspects of geometry, topology, index theorems, and a physics version of Hilbert's Hotel. In other words, this depends on the essential paradoxes of infinity, known as the quantum anomaly. All of these rely on the continuous nature of the field. It may well be that our failure is telling us something important about reality. Tong is doing something different from what I'm doing. He's taking a continuous theory and trying to represent it in a discrete way, and that's where his problems come from. He's representing an infinite theory by a finite one. And so what he's saying does not undermine what I'm saying. That's because what he's doing is different than assuming that the fundamental theory is finite. I just want to briefly comment on infinities and quantum theory in David Deutsch's writing in his version of the many worlds proposal, and I know that there are many other versions. But David Deutsch, to get a specific outcome from a specific situation, needs uncountable infinities of fungible particles. And this is described by Ellis. About this, Deutsch proposes that before a measurement, the photon is not just a single particle, but an uncountable infinity of identical or fungible particles. After interacting with the reflector, an infinite number of fungible photons exist in both output channels, but the ratio of those infinite numbers is finite, so that it has a measure proportional to the squared modulus of the wave function. Even though the observer knows they're going to evolve into two copies, they apparently assign relative probabilities to which copy they expect to become, given by the Born rule. You can see there, this is relying crucially on the paradoxical properties of infinity. The infinity isn't optional, it's essential. This won't work if you say there's a finite number. He emphasizes there repeatedly it's an uncountable infinity. And so this is the kind of thing which, in my viewpoint, should be excluded. It's not physics, it's not remotely testable, and it's the kind of infinity that tells you that you have gone astray, in my opinion. So, infinities of size the small. Is continuity plausible? Is there really a continuum of points with an uncountable infinity of points? I really don't think that makes sense. And so I think the starting point should be to start off with a discrete space-time and hence finiteness. Testing proving continuity is not possible, but we may see some possible hints of the discontinuity in the way that I've suggested. The alternative is discreteness and the emergence of apparent continuum by coarse graining. I haven't worked in this topic, but I'm thinking, from my viewpoint, this is the way to go in quantum gravity. One of the implications, by the way, is that fractals don't exist, because fractals only exist, if you believe strictly in a fractal, if it's self-repeating both in the large scale and the small scale, and this would chop the small scale, and so no genuine fractals would exist on this viewpoint. And one of the things this will do, it'll get rid of some of the divergences of the quantum vacuum, not all but some. So my final conclusion of the second talk. The occurrence of infinity is not provable by observation or as an implication of well-established physics. It may be useful in mathematics, but does not correspond to what actually exists. It certainly cannot be shown to be true by any possible observational experiment, and so it represents a breakdown of the theory. And so the take-home message that I've got is to distinguish between the essential and inessential uses of infinity. If it represents an arbitrary large number, larger than any physical quantity, then say so, use it in that way. If it represents an arbitrary small number, smaller than any physically relevant quantity, say so. Tell me how large, tell me how small, that's interesting. If it's genuinely infinite, large or small, depending on the paradoxical properties, I think this isn't physics, and we should not include that in our physics theory. So the universe may or may not stretch on forever, but the bit we can deal with is finite.